Okay, so let me start by setting the state, what type of nonlinear response I will be talking about. So generally, there are different types of nonlinear response one can think about. One is like nonlinear transport, which is zero frequency response. Another one is finite frequency, nonlinear optics. There's also something that brings you far away from equilibrium that I won't be talking about today, but this is like, for example, pump probe spectroscopy, where you heavily pump the system and then you see it looking, you watch it relaxing back to equilibrium. And then what I will be focusing on today is a technique that's called two-dimensional coherent spectroscopy, where you weakly interrogate the system, but with multiple pulses, that is still probing the equilibrium state of the system, but in the nonlinear regime. So I will start with three basic concepts and properties of nonlinear response that are worth remembering. The first one is that nonlinear response is described by higher rank tensors. This sounds a bit trivial, but has important implications. So here's an example. If you, for example, induce a polarization by an electric field, the linear response will be the dielectric susceptibility, but then there are higher order responses if the electric field is strong, like in a laser. And obviously you have higher rank tensors they obey different symmetry constraints than linear response. And sometimes, that allows you to learn something about the symmetry of the system without knowing anything else. You don't need to know what type of order parameter breaks the symmetry, for example. So this is a way to detect symmetries or detect symmetry breaking that is just using like the form of this tensor. And that has been used successfully by many groups, for example, by testing the second harmonic generation tensor and the structure of that tensor and relating that to symmetry. Another basic concept or properties is that this nonlinear response probes the topology and the quantum geometry of materials, and these are properties that we're very interested in. And they probe these properties beyond the linear regime. So they give you sometimes more information about, say, the distribution of the Berry curvature or the distribution of the quantum geometry, the quantum metric in the Brillouin zone that is the linear response may be agnostic to. And an example is, the nonlinear Hall effect due to the Berry curvature dipole, a proposal that has been done a couple of years ago by Yang Fu and Inti Soderman, and that has been realized experimentally also. And this is a nonlinear Hall effect that's quadratic in electric field that probes the Berry curvature distribution. In particular, it will be finite if the Berry curvature experiences a dipole. So that means even though the Berry curvature may not have a monopole moment, so the anomalous Hall effect, the linear response may be zero. The linear transverse response will be zero, which is given by the total integral of the Berry curvature. You would still have potentially a finite nonlinear response when you have such a dipole, meaning that the Berry curvature is positive in one part of the Brillouin zone and negative in another part of the Brillouin zone. So there's no monopole moment, but it has a dipole moment, and so you can see that if you in the nonlinear response. And the third general property is that very often you can view a nonlinear response as a lower order response in the perturbed system. So this is one way to think about nonlinear response. And again, this Berry curvature dipole and nonlinear Hall effect is one example. Another example is you can have other types of nonlinear Hall effects, and one is due to the quantum metric dipole that had been actually proposed even earlier and has been recently also realized experimentally. And here the idea is if you have a PT symmetric system that obeys PT symmetry, the Berry curvature has to be exactly zero, but you could still have a quantum metric, and that quantum metric can induce a Berry curvature in an applied electric field. Meaning if you apply an electric field, you can think of shifting the Fermi surface a little bit, and then that can induce a Berry connection, and the corresponding proportionality is this Berry connection polarizability, which is proportional to the quantum metric dipole. And once you have an induced Berry connection in an electric field, that can then give rise to an anomalous response in another electric field if you want. So then again, it gives you an E² response, and you can think of this as the system is being perturbed by the first electric field, and the second power probes that perturbed system. Now, a similar example is what I will be focusing on, and mostly is this 2D coherent spectroscopy, where you think of having multiple systems interrogating multiple pulses interrogating a system, and the first pulse or the second pulse, let's say they basically prepare the system in a non-equilibrium state, and then you probe it in that non-equilibrium state, or in this excited state, let's say. And pump probe, of course, is a highly nonlinear example of this, where you dump a lot of energy and you're probing this highly nonlinear, highly non-equilibrium state. Okay, so I have one slide about why, just to summarize, why would you probe quantum materials nonlinearly? I said it gives you additional information about the symmetry of a material and thereby also symmetry breakings that may have occurred. And one example is inversion symmetry breaking, for example, that opens up additional channels that were disallowed in the presence of those symmetries. That's the most dramatic example. It gives you access to the topology and quantum geometry of the Bloch wave functions that are hidden in the linear response. And also it gives you information about lifetimes and couplings of excitations. And I'll discuss that in the remainder of the talk. Okay, so this work was done with not only by me, but what I will talk about today mostly was done by my graduate student, Yehua Qiang from Iowa State. He will graduate next year. He's a very strong student. And my two postdocs, former postdocs, Victor Kido and Thais Trevisan, that worked with me at Iowa, they both will move to Brazil. They recently got positions there, so I'm very happy about that. And with my long-term friend and collaborator, Matthias Scheurer. And although I won't talk about experiment that much today, I have a couple of experimental collaborators that teach me about nonlinear response in real life. Okay, so with this, I want to now switch to this two-dimensional coherent spectroscopy, and I will start by explaining in more detail what that actually is. So as I said, the idea is to probe a system non-linearly, but very controlled by applying several time-spaced light pulses to the system, and then you measure an observable. And so basically, instead of from the linear regime, right, you can think of just having one pulse. Let's say here, this is the example for magnetic field and measuring the magnetization, but you can also think about other fields, electric fields, and probing other observables, but I will use that example here. So you have a magnetic field and probing the magnetization, the linear response would be the magnetic susceptibility. But if you apply two pulses, as shown on the lower left here, you have a pulse at 0, and then you wait for some time t1, you have a second pulse, and then you wait for some time t2, and then you measure. You're going to probe a different correlation function, which is just, if you want to use Kubo, it's just going to be described by a higher order correlator. So it's still probing the equilibrium state. So these higher order correlators will be evaluated in the equilibrium state, in the initial state, but you have to you have to compute a higher order correlator. And one way to rationalize this concept has been developed. It's called quantum pathways. So let me take a few minutes to walk you through what quantum pathways are, because they give you a very useful, they provide a very useful intuition about a nonlinear response. And one way to think about this is like, so to make sense of this quantum pathway, it requires knowledge of all Hamiltonian eigenstates. Obviously, we don't always have access to all Hamiltonian eigenstates in the correlated system, but conceptually, we can always think about it this way. So it will be basically the Lehmann representation of these higher order correlation functions. And I'll walk you through the example of linear response, and then it's easy to generalize this to a nonlinear. So in the linear response, right, we will compute that with a Kubo formula. So meaning we have a commutator, we have to compute these two expressions here, where for simplicity, I prepared the system in the ground state, but you can also think about it any thermal state. And so, you have to apply an operator, let's say the magnetization at time 0 to this state. And this is depicted here as this dot. So initially we have the ground state, and then we apply some operator, let's just see the magnetization at some time t0. And what happens, of course, is that, it can make a transition of the ket to some state I. Whenever there is a finite matrix element of that operator from the ground state to some excited state, this state will show up now. Now, basically, I've created a coherence in the system. There's the density matrix now is in an off-diagonal state, and the system will, acquire phase, which is proportional to the e to the minus ei minus e0, the energy of this state that you have created. And the transition matrix element gives you the probability of reaching that state. And then, as I said, you're going to get this phase. So you wait some time t1, the system acquires this phase, which is given by the energy difference between I and 0. And then you probe, you basically apply another operator, which in this case is just magnetization again. A and B refers to like X, Y, Z. And that has to bring you back to the ground state here because of this trace condition when you compute the Kubo formula. And so there's another matrix element, and then you sum over all the eigenstates. And this is how you, so then you have that part, and then you have the opposite part of the commutator where you make a transition of the bra state. And then we just draw a dot here. So you have these two quantum pathways, you add them up, and to get the linear response, and you can do a Fourier transform, and this is what you, this is how you compute the linear response in frequency. So obviously for this linear response, it's overkill to introduce this diagrammatics, but if you have higher order commutators, it gives some structure and some intuition about what are the different processes that are happening. And so for the second order, we get these 4 diagrams where either you basically have only transitions on the ket states, or you have transitions in both ket and bra, or only on the bra side. Then we can go to third order where you have like, even more. And so one important thing let me point out is this what's called a 2Q pathway, where you can imagine that what happens if you have 2 applications of that operator, there is a state J here, which is not connected to the ground state. So you're going to probe. So in that, and during that time T2, the system is potentially in a state with, let's say, 2 excitations. So it's not connected to the ground state. So really probing new states in this technique. And so, for example, if you could imagine, let's say you have 2 excitons, but they interact. The phase acquired during this time T2 is not just the sum of the phases you acquire with single excitons. So you can get some information about interactions of quasiparticles. There are also echo pathways where, like, phases that you acquire during one time evolution will be exactly canceled for some of these during another time evolution, and that can be used to look through inhomogeneous broadening and learn something about the intrinsic lifetime of particles. Okay, so then again, you could think of this as in real time, and in the end, you go to frequency space. Now, since I had like multiple time intervals, obviously I'm going to get multiple frequencies, and this is why this is called 2 or higher dimensional spectroscopy, because in the end, you're going to get a response that depends on many frequencies, and typically people use 2 frequencies and they set all the other times to fixed. So in this sense, we would vary, let's say, T1 and T3, and would set T2 to be 0, for example, and then we would do a Fourier transform to get omega-1 and omega-3 and plot the response as a function of omega-1, omega-3. So that would be a 2D spectrum that I will show later. So this can be done experimentally, and I have just because of lack of time, I only have like a few slides. So this, I was not involved in that, but just to see that this is not just pure theory. And this is a nice experiment in Keith Nelson's group where they probe a very simple system that just, it's a magnetic system that has 2 terahertz active zone center magnon modes. And they, by choosing the polarization of the magnetic field, they can only probe a particular one. So here they probe this antiferromagnetic one. And the idea is you really send in several terahertz pulses, and you're interested in this nonlinear part of the response, which is meaning you are looking at the response in the presence of both pulses, and you subtract the part where you only have one of the 2 pulses present. And so it's really a time domain technique, meaning you measure the magnetization at some time t in the presence of these pulses, and in the end you subtract the time traces from each other, and you do a Fourier transform to get this like omega-1, omega-2 spectrum, and you get certain peaks which you can identify with these different pathways. So really you can see in this experiment nicely that the system can undergo different evolutions, and you probe all of them at the same time, of course, but here they're nicely separated. One of them, for example, is this 2Q pathway, where after in the second time interval, the system has 2 magnons, and so it oscillates with twice the frequency of a single magnon. Okay, there are other experiments that I won't be talking about in Armitage's group and Jeremy Johnson's group, and so this is something that experimental groups are building up, and so there is really hope that this can be a new technique to interrogate correlated materials. With this motivation, let me talk about the theory work we did by computing this 2D spectroscopy of the Kitaev honeycomb spin liquid. The honeycomb spin liquid is the ground state of this honeycomb spin model, and here we are looking at the honeycomb lattice. So we have this Ising type interaction, which every spin has 3 bonds, and we put different Ising interactions on the different bonds coming out. So sigma XX on an X bond, which is the black line. There's a Y interaction here and a Z interaction here. So this can be exactly solved in terms of static Z2 fluxes and Majorana fermions. And this is an example of a quantum spin liquid where we know where we can solve this. We can solve it exactly. It has these fractionalized excitations in terms of static visons and Majorana fermions. And in the end, you're going to get a Hamiltonian, which is quadratic because all the fluxes are static. So you have different flux sectors that you can all diagonalize. And This is the phase diagram from Johannes Knolle's thesis, where you find different spin liquids. Here we're focusing on this B phase, which is a gapless spin liquid. The spin correlations are only on the nearest are very short range, and there's a flux gap and the gapless Majorana matter excitations. So now, I mean, there are also material candidates for these magnets, but they always show additional interactions, but they're hard to deal with in theory. So for this work, we started with just the pure Kitaev model. But of course, the motivation for this work is to include other type of interactions and see the signatures or the differences of the signatures in the 2D response were for the pure Kitaev model and the one that has additional interactions. So that's obviously just the first step because the idea is to eventually perform experiments on these magnets and see whether there are any signatures of the Kitaev model showing up. But for this, we need to know what are the signatures of the pure Kitaev model in this response function. There was this beautiful work from Johannes Knolle and collaborators some years ago to look at the linear response of the Kitaev model, which already is very unusual. So since I introduced this pathway, this would correspond to computing this type of pathway. And so it's really just it's a linear response spin-spin correlation function. And again, you can think of this as computing this in the Majorana in the Lehmann representation. So you have these two matrix elements. You have the ground state. You apply a spin operator. You get some excited state, and you apply another spin operator, and you have to go back to the ground state. And in the intermediate state has a flux pair, because if you apply a spin operator at a given site, then it creates a vison pair nearby. And because of that, the response will be gapped. And so even though you have gapless excitations, gapless Majorana excitations, because you're probing a spin-spin correlation function that you have to excite a vison pair, this will be a gapped response. And you can read off the vison gap energy from the neutron scattering. So here's the response of the neutron scattering in the isotropic model as a function of frequency. And you see that there is a gap which is equal to the turns out to be equal to the two flux gap. Okay, so then the question is there anything else that shows up, or more signatures of the excitations in the nonlinear response? So there was some nice work from Youngbaek Kim's group some years ago about the third order response. So they computed this third order response in the 2D spectroscopy, and it looks pretty complicated. It has several signatures that you can associate with these pathways. But since in terahertz, one of the difficulties of this terahertz 2D spectroscopy is that all these different pathways appear on top of each other in the spectrum, because you cannot distinguish the different pathways in the propagation vector. So, but I won't go through the details of this, but you can associate these different signatures with different pathways and different processes in the system. But what we realized when we were working on this is that also, in fact, so they only looked at the ZZZ component, and we realized that actually there's a second order response and this YZX, which is also finite, which lower order response is experimentally easier accessible. There are fewer pathways to compute, so also the results will be more easily interpretable, the theoretical results. So that's what we looked at. So if you look at this second order response and this off diagonal value, let me first walk you through why it can be finite. This is because you first apply an X operator, which creates a flux pair across, let's say, the X bond. Then you apply a Z operator, which creates a flux pair across a Z bond. So it basically flips this here. And in the end, you have to remove that flux pair again. So you have to apply a Y operator. So that can bring you back to the ground state. And you couldn't do that with like, let's say, 3 Z interactions, because you always end up with one flux pair in the end, which is why the diagonal response would be 0, which is already kind of a signature of this type of exotic interactions, that some components are 0, that may be non-zero for Heisenberg and so on. Okay, so we have in the second order, we only have these two pathways, which is which means we start from the ground state. We apply an X operator, we create this flux pair and also some Majorana excitations. And then we apply a Z operator, we have another flux pair, and we will also make a transition potentially to some other Majorana excitation, and then we go back to the ground state. And we acquire these phases in between. So what can we learn from here? what we can learn. So first of all, let me show you the result, and then we look in detail what we can infer from this response function. So when you look at this from like, on high level, you see like something happening along the x-axis, something happening along the diagonal. Here, this is a function of omega-1 and omega-2. So these are the two frequencies associated with the time difference between the first and the second pulse, and the second pulse in the measurement. And overall, you see that this obeys the symmetries that you have. The interesting thing, or the useful thing in the second order response, is that you can see that you can easily see theoretically that this will be one of the pathways and this will be another pathway. So this is much easier than the third order response, where the pathways were all on top of each other. So here we can, this is much easier to interpret what happens here, because they're clearly separated. So looking at a broader frequency range, we see that really the dominant response happens at low energies. So that's also something, even though the bandwidth is larger, really the dominant response is like at the edge of this at the two flux edge here, two flux gap edge. So let me look at the R1 pathway in detail. So this is just one pathway now, but as I said earlier, you can easily distinguish them. But I removed the contribution from R2, which was along the x-axis here. And so we see several peaks here, and we also see some off-diagonal peaks. And so the peaks along the diagonal are basically the same peaks that you already find in linear response. And so the interesting thing is that we find these off-diagonal peaks. And the off-diagonal peaks, to interpret them, we were looking at the wave functions, the Majorana wave functions that are very localized. So you can quantify that by the IPR, by the inverse participation ratio, which is defined as this. So you can basically, by computing that, you can figure out which Majorana wave functions are more localized than others. And so we basically see that the localized ones live at low energies, and they are actually localized around these vison pairs. And in the gray dots here are the energies of these localized Majorana wave functions. And you see that these off-diagonal peaks that appear are associated with these localized Majorana wave functions. And so the off-diagonal peaks are actually proportional to the overlap of these localized Majorana matter states. And so these off-diagonal peaks can only occur if you have some localized eigenstate of the system, because otherwise, there wouldn't be a large overlap between two eigenstates. If they would be like very delocalized in the system, there would be only a very small overlap. So the fact that you have off-diagonal peaks is very qualitative insight that the underlying wave functions must be localized, because we are applying a local operator in the response function. So I'm saying this because obviously we're trying to find signatures in this nonlinear response that are kind of not very model specific. So we try to because if you do an experiment, you may not know the underlying model that well. So it's important to see what features of this response function can be robustly associated with certain properties of the system. And so these off-diagonal peaks can be robustly interpreted as localized excitations because you're applying local operators when you compute that response function. Okay, so with this, I'm at the end. Let me conclude and summarize. Nonlinear response functions are powerful probes of quantum materials. They can detect symmetries. They can reveal hidden orders and symmetry breakings. They can map out the quantum geometry. I haven't talked about this in detail, but I have at least stated that. And that means they can tell you something about the Berry curvature and the quantum metric in the Brillouin zone. They can access properties of quasiparticles such as lifetimes and couplings and wave function overlaps. So they give you additional information about the nature of the excitations in the system, which is something we're very interested in. And in our case, they were also a probe of the fractionalization of quantum magnets. So there was a clear distinction between the role of visons and the role of Majoranas. Let me end with a couple of open questions and theory challenges. One thing is very interesting, of course, would be to look at nonlinear response in other correlated and also disordered materials, where potentially we don't have access to all the energy eigenstates, and where you have to use Green's functions. And obviously, this is the direction that's very interesting to go. Other materials where you couple with the electric field may be also experimentally easier accessible, like multiferroics and superconducting systems, and those experiments are being underway. And the question is, what can you learn about, let's say, superconducting pairing or excitations in superconducting systems that are inaccessible by linear response. And the last one is also something we're working on. You can also combine this nonlinear terahertz with Raman spectroscopy, or you can just do nonlinear Raman. And this just opens up a whole new toolbox of probes that experimentalists can do and that theorists can interpret. And so this is an interesting field and direction to go that is widely open, I would say. So yeah, this work here is posted on arXiv, and yeah, I'm happy to take any questions. Thanks a lot.